Welcome to the first day of the rest of the class. We're about 40% done content-wise. So now that we've learned everything there is to know about intermolecular forces, we're going to combine it all and figure out how surfaces and nanoparticles interact with each other. So a few things are going to change for us. Now when we draw nondescript spheres, we're no longer talking about atoms and molecules. We're talking about surfaces and nanoparticles and microparticles, which are separated by some distance d, big D. Don't ever call me that, as if you were tempted to. R goes to big D. R formerly meant the center-to-center distance between atoms or molecules, and now it means the surface-to-surface distance. And they are characterized by, the interaction potential was characterized for atoms and molecules as small w of R. But for surfaces, we're going to remind ourselves that we're talking about big objects, not just atoms and molecules. So we're going to use a big W and the big D. Just like for intermolecular and interatomic forces, we had attractive and repulsive interactions. We had attractive forces that were derived from electrostatics, and maybe like the Coulomb force, the dipole-dipole force, the dipole-induced dipole force, but also due to quantum mechanical effects, like a rotating dipole around a rotating electron around a nucleus, which gave you a rotating, quasi-rotating. We modeled it as a rotating dipole, which was transient. That's a quantum mechanical effect that gave rise to these transiently polarized interactions. We induced dipoles in nearby molecules and caused an attraction. We also had repulsive forces, like the force due to the Pauli exclusion principle, which gave us the big increase in potential energy as we approached the R equals 0 separation, so the repulsive force went way up. So similarly, in the case of interparticle forces and intersurface forces, we're going to have attractive forces, repulsive forces, and we're even going to see some actual oscillatory forces. Which go alternating attractive and repulsive as the distance in between the surfaces increase. The first attractive force that we're going to find is an ensemble of van der Waals forces. So if you take every molecule in this sphere and you integrate the interaction with every molecule in this sphere, we get a van der Waals force that is the combination of all three van der Waals forces, the Keeson, Debye, and London forces, that we're just going to ball up into one force that we're just going to call the van der Waals force. In some solvents that permit ionization, so ionization of surfaces, surface charges, surfaces that are formally uncharged become charged in a certain solvent. Water is the best example. Water is the biological example. It's what we're talking about 99.9% of the time when we're talking about this particular force. So suppose we have these charges that are very close to the surface, that are bound permanently to the surface. We have counterions. that form a diffuse double layer between these particles. And the diffusion of the double layer, which is entropic, despite the Coulombic attraction, there's always some amount of diffusion if the charges are small and somewhat mobile, is going to produce an entropic repulsion when you try to bring these big particles together, because the diffuse layer is going to be compressed in between the big particles and it's going to force them apart. And that's called the electric double layer, or EDL force, and that's repulsive. There's a little bit of analogy to the van der Waals force and the repulsion due to the Pauli exclusion principle, except that the van der Waals force always dominates at contact. Whereas it always dominates as the separation goes to zero. Whereas as the internuclear spacing went to zero, the Pauli exclusion principle dominated. So in interparticle forces, when they're touching, that leads to a strong interaction that's dominated by the attractive force. Whereas in intermolecular and interatomic forces, the repulsive force dominated as the separation went to zero. Does that make sense? We'll show mathematically why that is later on. We have other types of repulsive forces as well. So oftentimes we have particles that have polymer chains on the surface. And these polymer chains are free to flop around. They have a lot of configurational entropy when they're separated. When you push them together, the polymer chains collapse because they can't move around so much, and you get, again, an entropic repulsive force. So this is steric polymer mediated. Incidentally, the electric double layer force and the steric polymer mediated force, that seems crazy, right? Like, how often do we have these fuzzy nanoparticles? Well, it turns out if you have a biological system where your lipid vesicles or protein complexes, lipid complexes have sometimes if everything attracted every time, then your cell, which is just like a huge amount of, like a hugely concentrated solution, right, of all these organelles and proteins and nucleic acids and lipids, you would just expect everything to just collapse. We would all just collapse into a black hole of muck, right? But we don't do that, and we don't do that because of these steric repulsive forces. This is incidentally the combination of the EDL force and the steric polymer mediated force, or why milk is a stable colloid, for example, because the milk fat globules have these diffuse charges and also these diffuse polymer chains. So let's draw a new, glad we're not doing this, that looks hard. So we can have other types of forces between particles as well, and they're going to depend on the environment. So suppose you had two flat surfaces, and you had solvent molecules that were neatly packed in between. And again, the separation here is capital D. As you bring these flat surfaces together, you'll push out the molecules of solvent in between, but you'll push them out in steps because there will be some disordered phase, and then it will crystallize again, quasi-crystallize again. And you squeeze it a little bit more, and a little bit more, and so on. It's like taking, anyone ever taken a box of pencils and tried to like squeeze them and they kind of shift like this? It's like easy, hard, easy, hard, easy, hard, easy, hard, easy, hard to push like cylinders or pens or pencils together. This is actually happens on the molecular scale if you have spherical or cylindrical molecules and flat surfaces, and that gives you a force law that's oscillatory, and this is solvation. We'll find that solvation forces, so this is, or we call this an oscillatory solvation force to differentiate it from repulsive solvation forces and attractive solvation forces. We're not going to worry too much about these. It's really most interesting to consider the oscillatory force because it's really a way of measuring molecules and the effects of excluding small molecules from a gap, from a nanoscale gap. Now suppose we have these same two flat surfaces, but we're no longer in a solvent, we're just in a humid environment. And the humidity causes a meniscus to form. And the meniscus that forms is a result of the surface tension of water, because water wants to maximize its van der Waals forces, including hydrogen bonding, which is a especially strong form of the Keesom force. So if you extend these surfaces apart, the meniscus behaves a little bit like a spring. Not exactly, doesn't follow the same force law as a spring, but it tends to want to bring the surfaces back together. And this is called a capillary force. It's the force that's responsible for sand castles, how sand castles work. It's the force that's responsible for the disgusting, sticky feeling that we have on hot days like this week. Toward the end of class, right before the final exam, we'll talk about how these forces lead to self-assembly of particles and particles on surfaces. So we'll spend a lecture on the thermodynamics of self-assembly, and we'll also spend a lecture on how intermolecular forces and solvation forces give rise to friction phenomena. So how we don't slide across the room into the wall, how friction slows us down, how friction produces vibrations and music and everything. And we won't talk about music, but vibration does produce music. Okay. So this is part 2 of the course. Surface forces, and surface forces could be the surfaces of nanoparticles, microparticles, proteins, drug delivery vehicles, photoresist films, solar cell, light absorbing layers on their substrates. It could be anything. So what are the abstract principles that we'll encounter in this part? So what's characteristic about a surface? Well, the molecules at the surface are lonely and want friends and have a high potential energy. Just like an isolated charge is kind of upset, molecules at a surface are kind of upset. So they really want to be in the bulk. They're upset about not having having unsatisfied bonds, which they need for a fulfilling life. Molecules at surfaces have unsatisfied bonds, or if we want to be sophisticated, unsatisfied valencies. So if you picture two molecules, and we're just going to abstract the bonds with the neighbors using these arrows, these arrow-like arrows. This one is completely satisfied, this one is not. Suppose this is the gas or vacuum phase, and this is the solid or liquid phase. These bonds could be ionic, covalent, metallic, van der Waals. The unsatisfactoriness of the reduced valencies of atoms and molecules at the surface lead to something called a surface free energy or an interfacial free energy, or in the case of a liquid, that manifests as a surface tension. So a surface tension is a force, or it's also the surface energy density. And the surface tension is in units of force per unit length. Now suppose we had how do you measure surface tension? Suppose we had a wire frame and we had a movable rod. And suspended within the wire frame and the movable rod is a liquid film. And we're going to presume for a moment that this scenario lasts long enough to measure an effect. So the liquid film won't be stable there for very long, but maybe if it's got some surfactant in there, it will be like a children's bubble blowing wand. So you have a liquid film in here. We'll call this the x-axis. This will be our length L. Now the surface here, this is a thin surface, so it's mostly, the molecules in this film are mostly at the surface. So there's going to be an inward pull of 2 gamma, where gamma is the surface tension, which is a force per unit length. And where did the factor of 2 come from? There are 2 sides. So there are 2 sides in this experiment. So we have the relation where the work done in translating this rod toward the surface tension, done by the surface tension, is the force, the integral of the force times dx. or the integral of 2 gamma L dx. And where did the force come from? The force came from the fact that it takes work to force a molecule in the bulk of the liquid film toward the surface of the liquid film. It really doesn't want to be at the surface because it has all those electrostatic or ionic or metallic bonds in the film. It doesn't want to go to the surface. The molecules don't want to go to the surface. So that's why they produce this restoring force called the surface tension or surface energy density. Surface tension has units of millinewtons per meter, or you'll see sometimes dynes per centimeter. This is MKS units, and this is CGS units. Conveniently, it doesn't matter which one we use. They both give exactly the same number. So as a result, when you see surface tensions and surface energy densities, often they don't even give you the units because 72 is the same in millinewtons per meter or dynes per centimeter. So let's look at some examples. Water, 73. Ethanol, higher or lower than water? Lower, why? So polarity is probably similar, but it's missing one of its hydrogen bond donors because it only has one OH bond, and it goes way down for ethanol. Ethanol is also booze. This is glycerol. We get some of our ability for hydrogen bonding back here. We also have more van der Waals forces because we have more carbon atoms. So surface tension here is going to go up, but not as much as it does for water. Now, how about, anyone ever see Terminator 2 Judgment Day? So there's a very high surface tension character in that movie, made of a mimetic polyalloy, the T1000. Mercury, high surface tension or low surface tension? And I guess nowadays no one ever actually sees mercury because of how dangerous it is. But if you were to break an old thermometer that has not been confiscated by the feds or OSHA, and you pour it out onto a surface, you get a blob of mercury that looks like a sphere. Why does it look like a sphere? Because the sphere is the way to pack in the most molecules into the bulk without exposing them to the surface. So it has a high ratio of volume to surface area, much like the Blanton's whiskey bottle. Surface tension here is really high. .485. So we can see some trends. So I'm gonna, just because we like formamide so much because of the exam, I'll write it on here somewhere. High or low? Quite high. 58. Okay, so we can see surface tension is a strong manifestation of intermolecular forces. In the case of metals like mercury, the electrons are actually shared between atoms, and a metal therefore has very strong interatomic forces through this phenomenon of metallic bonding. So this looks like a good manifestation of intermolecular forces, and it is. But what quantity have we met earlier in the class that's also a manifestation of intermolecular forces? I'll let you think for a moment while I answer this question.
So is surface tension a result of molecules' anticipation in bulk that is going into the surface? Or is it the molecules at the surface which want to get into the bulk?
I like the word anticipation because that's a very philosophical point. Every infinitesimal step of the way that brings molecules closer to the surface is unfavorable energetically. It raises the potential energy of the system, and there's therefore a driving force to go in the other direction. So whether we can call that anticipation or just the way it is, we can make that determination on our own, whatever we're comfortable with, I guess. I like anticipation because I like imbuing atoms and molecules and materials and biological molecules as having like intent, even though that's probably wrong. It helps me understand things. There was another thing that we learned where we took all the intermolecular forces and we put some dimensionless number on the board and said, aha, high this. What was that? Or low this? Dielectric constant. What do we think is a more holistic representation of intermolecular forces? Surface tension or dielectric constant? To some extent, it seems like they should scale with each other, right? But not necessarily. While they are related, surface tension is a result of the intermolecular pair potentials, whereas dielectric constant is a result of the strength and density of dipoles with some contribution of intermolecular forces. So can we imagine a scenario in which the intermolecular pair potentials increase, but the dipole stays the same and the density goes down? And if we think about straight chain alcohols, so this one is 1, 2, 3 propanol. This is, oh God, 1, 2, 3, 4, 5, 6, 7, 8 octanol and a lot more enol. We have surface tension that is going to increase or decrease. Okay, let's go back. Let's go back to the first part of the course. The dielectric constant. Dielectric constant will increase or decrease as we go from here down to here. I heard a lot of crease. To me, that could be either one. High to low dielectric constant because of density of dipoles. 20, 10, 8. Big difference. How about the surface tension? Surface tension, remember, you get like a kT or so per CH2 bond, and for an intermolecular pair potential. So we have, which has the stronger intermolecular pair potential? This with this or this with this? Bottom, right? Because there are just so many more bonds. So it takes more work to take one of these molecules into the surface because this one has a lot more van der Waals bonds, and the contribution due to hydrogen bonding is the same. It's the same in every case. So the surface tension actually goes up. 24, 27, 28. So which quantity is a better predictor of overall intermolecular forces? probably the surface tension, even though it's certainly a factor in determining the dielectric constant as well. So the surface tension is actually responsible for lots of phenomena. You can basically think about the way you feel right now. There's probably some surface tension somewhere that's affecting the way you feel. But it's responsible for some more conspicuous phenomena in nature as well. For beading and spreading. As in rain-X on a car window. So you have either beading behavior. So beading is like this on a surface of a liquid droplet on a surface, and spreading is like that. It's also responsible for capillary flow. Like when you put a straw, like a thin straw, that's transparent in a drink, and the water partially goes up the straw. You take a glass capillary tube, maybe the water goes way up the straw. You take a tree that has cellulose inside of it, and you water the tree, and the water travels up the trunk of the tree. Also, a water strider. We don't really have water striders in California, at least not that I've seen. Well, at least probably not in San Diego County so much. I'm sure I'm wrong about that. It's a good thing this isn't recorded. Water striders are those arthropods that sit on the surface of ponds and slow-moving streams that skid across the surface. And imagine that this is the that this is a water strider's foot, and there's some downward force due to the weight of the foot. But then you have a force that's kind of tangent to the intersection between the foot and the water surface. That's the force due to the surface tension. And if you resolve both of these along the vertical axis, you get something that counterbalances the downward force. What would happen if you took a water strider and you put a little soap in the pond? It'd be sadistic, but if you wanted to do that, the water strider would sink. Why would the water strider sink? Why is surface tension reduced by the use of surfactants? SDS, sodium dodecyl sulfate. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 sulfate. What can we say about sodium dodecyl sulfate? On your shampoo bottle, this might say Laurel, sodium lauryl sulfate, after lauric acid, the fatty acid from which it's derived. We have a hydrophobic tail group and a hydrophilic head group. And what happens when we put this in water is, one, we want to lower the surface tension of the water we want to lower the interfacial free energy of the water, so the hydrophobic tail groups will point toward the surface, and the ionic charged group will point inward toward the bulk, because water has a high, because this group has a high Born energy, and the water molecules will reorient around this in order to solubilize it. So we have in one case, we don't care what the surface is yet, but suppose this is the pure water case. Where the water molecules are arranged at the surface to maximize their hydrogen bonding with the bulk, but still we have unfilled valencies at the bulk. These water molecules are not happy, so it balls up to some extent in order to balance all of the energies, the energy of the water with the solid, the water with the gas, and incidentally the solid with the gas. But when we add SDS, we get a much smaller contact angle, and that's because what I'm drawing here is SO4 minus. The hydrophobic tails stick out. So once we add enough SDS to coat the surface, to form this monolayer at the surface, if we add more SDS, it doesn't change the surface energy very much anymore. In fact, it doesn't really change the contact angle anymore because we've already saturated the surface. There's only so much surface area. Okay, let's look at the idea of this contact angle, which is a result of a triple interface. And contact angle the contact angle is this line that I'm always showing here. And the line is equivalent to the gas-liquid interfacial energy, not the contact angle. This vector is the interfacial surface energy between the gas and the liquid. Surface tension or energy. This is the surface, the interfacial energy. Same thing, it's just surface implies air or vacuum, whereas interfacial means solid-solid or liquid-liquid or liquid-solid. So this is the surface energy of the liquid-solid, and this over here is the surface energy of the gas-solid. So at equilibrium, if you project this down onto the surface and you add it to this vector, it should cancel out this vector at equilibrium. So at equilibrium, the forces resolved along the horizontal axis are equal. So we have gamma gas solid equals gamma liquid solid plus the projection of gamma gas liquid onto the horizontal axis. One of the problems with this equation is that the surface tension and the contact angle are easily measured. Because this is just a force and this is just an angle. Whereas, how are we going to get the gas solid and liquid solid interfacial energies? They're a lot harder to get. So we need a more I mean, we can calculate them theoretically by adding up all the van der Waals forces. But is there an easier way to make this relation work? So let's think about this problem in a little bit more of an abstract way, which always makes people excited. And then we'll bring it back to the case of liquids. So let's think about the work of adhesion, say the work of adhesion between the solid, or between the liquid and the solid, or a liquid and a liquid, or a solid and a solid, or the same solid and the same solid and the same liquid and the same liquid. This is the work of adhesion or cohesion. It's adhesion if it's two different things, it's cohesion if it's the same thing. So imagine two blocks of stuff. These are condensed phases, beta and alpha. In some non-condensed phase of gamma, so say gas or vacuum. Actually, it could be a liquid too. We have some interfacial energy, gamma, alpha, beta. And if we were to separate these two slabs apart, alpha and beta separated by distance capital D, we got rid of this interface, but we formed two new interfaces of gamma beta omega and gamma alpha omega. By convention, the gammas are positive. The work needed to accomplish this separation is equivalent to the differences in interfacial energies before and after. The before state and after state. The work, so this is the work of adhesion or cohesion, is minus or plus alpha beta plus or minus gamma alpha omega plus or minus gamma beta omega. The bottom convention is more typical. And the more typical convention, but you'll see both in books or in the literature. So just know what the reference state is. In the case of the bottom reference state, it's the reference state where the energy at infinite separation is 0, and that's what we're used to in the course. So that's what we'll keep. Suppose beta and alpha are a column of the same liquid. If a column of a homogeneous mixture or pure liquid, we can say that alpha and beta are equal, and gamma alpha beta is 0, because how can you have an interfacial free energy in a homogeneous medium? There's no interface. So that allows us to simplify the work of cohesion. So we have W alpha alpha equals plus or minus 2 gamma alpha omega, or equivalently W beta beta equals plus or minus 2 gamma beta omega. To make things less abstract and connect this back to reality, suppose, as in the case of a contact angle of Rain-X on a windshield, we had the gamma phase as the gas, alpha phase is a solid, beta phase is a liquid. Then we have the work of the solid liquid equals minus gamma solid liquid plus gamma solid gas plus gamma liquid gas. Where this thing, which is the stuff we don't know from over there, is equal to gamma gas liquid cosine theta, and we can rewrite this as the work of adhesion between the solid and liquid equals gamma liquid gas, which is just the surface tension, times 1 plus cosine theta. So now we can measure the work of adhesion, the interfacial energy between these two surfaces, which is quite useful in determining the wetting properties of solids, based on the surface tension, which we can measure, and the contact angle, which we can measure. And this is called the Young-Dupre equation. We're going to find that we can use this relation to calculate the rise of a column of liquid in a capillary. We can use it to predict the wetting and spreading and beading behavior of surfactants on a surface, of liquids on a surface, and it's going to be useful in a number of other ways. Next class, we'll talk about the first part of the van der Waals force between surfaces, which is adding up all of the different van der Waals forces, so integrating the interactions of one molecule into another, from one surface into another surface, and we'll build up from there. Now we'll turn off the camera so we can go over the exam.